One and all, today we will discuss about the direct stress and bending stress. Direct stress and bending stress. Simply we represent this direct stress and the bending stress. Simply it is called combined stress. What do you mean by the direct stress? Direct stress means the axial load per unit cross sectional area. This means the axial load per unit cross sectional area. That means the axial load per unit cross sectional area. It represents or it measures simply Newton per mm square. Newton per mm square. The stress distribution of this direct stress is we take a simple section, that is a symmetrical section, rectangle section, breadth B and depth D. The neutral axis of this rectangle section NA, this is a symmetrical section. The stress distribution of this rectangular section is uniform. Throughout the section, the stress distribution is uniform. This is cross section and this is stress distribution. The next topic is bending stress. The next topic is bending stress. What do you mean by the bending stress? The bending stress is introduced or obtained from the flexural equation. This is the bending stress is obtained from flexural equation, or simply known it is as bending equation. The flexural equation is m by I equal to sigma b by y or E by r. In this equation, we require only these two terms. That means simply m by I equal to sigma b by y. So we require bending stress. So simply we have to write sigma b equal to m by I into y. This simply represents I by y. So m, what is meant by I by y? I by y is represents, we already know about this. Already we learned about in previous section of strength of materials 1 from third unit of bending equation or shear stresses. So we already discussed or learned about SM1. So I by y means Z. That means section modulus or modulus of section. So simply it is bending stress. Bending stress are obtained like this. Okay, then stress distribution of bending. Stress distribution of bending, same as take a rectangular section. This is depth of the section and this is width of the section. These are the cross section of the rectangular section. The stress distribution is like this. This is the neutral axis. Sigma compression, sigma tension. That means the bending stress at neutral axis is 0. Bending stress at neutral axis is sigma b equal to 0. Bending stress at neutral axis is 0, but from neutral axis the extreme distance increases. From neutral axis extreme distance increases, stress also increases. From neutral axis extreme distance is increases, stress is also increases. This is the extreme distance in this way, and this is bending stress. Extreme distance increases, bending stress also increases. That means bending stress is directly proportional to the extreme distance. What is meant by extreme distance? The extreme distance means the distance in between the extreme, in between the neutral axis to the extreme fiber. This means this represents the extreme distance. Okay, as usual, from neutral axis below, we already learned neutral axis above. From here, neutral axis below, extreme distance increases, bending stress also increases. 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 That means B sigma BC is directly proportional to y. That means neutral axis above, which type of stresses will output? Compressive stresses. That means compressive bending stresses. Sigma BC. Neutral axis below, tensile bending stresses. Sigma B. Okay, we represent the same as sigma B is directly proportional to y. So the next combined stresses. Combined means both the direct stresses as well as bending stresses are combined and to form the which type of stresses? That means the resultant stresses. Here this is the stress distribution of direct stresses. We know about this. This is the stress distribution of direct stress. Direct stress simply represents sigma naught plus, here it is bending stress. Here it is bending stress. This is sigma C. This is sigma B. This stress distribution due to bending. This distribution due to bending. This simply represents sigma B. This is sigma naught and this is sigma B. Sigma naught is simply represent direct stresses and sigma B is simply represents bending stress. Both are combined. Sigma naught plus sigma B equal to resultant stresses. Equal to resultant stress. Simply it represents as combined stress. Simply it represents as combined stress. The stress distribution is like this. Here it is compressive sigma naught. Here it is sigma naught. Here it is like away from the section. Here it is 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 towards the section. It is equal to like this. Finally, we got this. Finally, we got this. Finally, we got it. Here it is sigma max. Here it is sigma minimum. Here it is sigma max. Here it is sigma minimum. That means sigma max is maximum stresses and sigma minimum is minimum stresses. These two stresses are obtained from the both the direct stresses as well as bending stresses. This is stress distribution of combined stresses, or simply it's known as resultant stress distribution due to the direct stresses as well as bending stresses. Direct stresses as well as bending stresses. Red simply represents in the form of equation sigma max equal to sigma naught plus sigma B. So sigma naught is simply represent load per unit area plus sigma B. From the Planck equation already we discussed M by Z. Simply P by A or M by Z means M by I by Y. Simply write into Y. Like this. Sigma minimum same as sigma naught minus sigma B. Same as finally P by A minus M by I into Y. This is. Then we go for the next section of eccentric load. The next we discuss or we learn about the eccentric loading. We learn about the eccentric loading. What is meant by or what is mean or what is the eccentric load? Eccentric load. What about the eccentric load? Eccentric load means simply the line of action of the load does not coincide with the axis of the member. We simply represented in diagram. This is a column. This is axis of the member. The line of action of load, that means this is the load. Line of action of load is in this direction. The line of action of load does not coincide with the axis of the member. The line of action of load does not coincide with the axis of the member. It is called eccentric load. What is meant by the eccentricity? What is meant by the eccentricity? It is simply represented small e. It is indicated by the small e. What is meant by the eccentricity? The horizontal distance between the axis of the member and the line of action of the load. It is called the eccentricity. This eccentricity is produced two types of stresses. Eccentric load produce or causes two types of stresses. Those two types of stresses are direct stresses as well as bending stresses. Direct stresses as well as bending stresses. The eccentric load causes two types of loads. Eccentric load causes two types of loads. Direct load as well as bending load. Direct load as well as bending load. Direct load means it is simply represented or indicated in P. It is indicated in M. M means moment of resistance. M means moment of resistance. This M equal to P into E. So P means transverse load into perpendicular distance. It is simply eccentricity. So how eccentric load causes the direct load and bending load? You can see this. It is simply in a diametric form. Take column or abstract column is simply this is axis of the member. Here it is P, it is eccentricity distance E. This is cross section of simply represents small a. This is a column acts with the eccentric load. Some eccentricity E that is under equilibrium condition, it simply represents axis of the member. Next load. So our eccentric load P, eccentricity E, eccentricity E. So here it is three loads. Here it is three loads: axial compressive load, axial compressive load, and axial tensile load. Counterclockwise of axial compressive. Here it is eccentric load. These three loads are split into separate forms. These three loads are split into separate forms. How it is split? That means it simply represents it is axial load P. Axial load P. These axial load P produce the direct stress. Direct stress means load per unit cross section area. Load per unit cross section area. So the next here, two equal and opposite forces form a couple. Two equal and opposite forces form a couple. The moment of couple M equal to force into perpendicular distance between them, small e. That means eccentricity. So these M produce, that means bending. M means bending or moment of resistance. This bending moment produces the bending stresses sigma B. These bending moment produce the sigma B, that means bending stresses. Bending stresses formula means M by Z. We know about M into M means P by Z Y by I. So here P into E by I into Y. So one eccentric load, that means eccentric load produces the bending stresses as well as direct stresses. These are like this. The next, the difference between direct stresses and bending stresses by means of diagram. We already seen how what is the direct stress and bending stress by eccentric load, and furtherly we discuss difference between direct stresses and bending stresses by means of diagram. We simply represent three diagrams. Okay, the first one here means sigma naught greater than the sigma B. Sigma naught greater than the sigma B. That means direct stress is greater than the bending stresses. Direct stress greater than the bending stresses. Direct stress greater than the bending stresses will form a uniform nature. Will form uniform nature. That means compressive nature. It forms a uniform nature. Uniform nature of stresses. That means compressive stresses. The next one, next diagram, sigma naught equal to sigma b. That means the minimum stresses are 0. Resultant minimum stresses are 0. The resultant minimum stresses are minimum. When it is formed means sigma naught equal to sigma b. Sigma naught means direct stresses are equal to bending stresses. When this condition, the minimum stresses of the minimum resultant stresses are equal to 0. The maximum stress sigma max, here sigma minimum equal to 0. This is the most important condition. It simply represents the no tension condition or middle third of the condition. This middle third of the condition help to produce to find the polar cap of the further we will discuss. The next third condition, sigma not less than the sigma b. Here it is sigma naught greater than the sigma b. That means produce the same nature of stresses. Then here it is sigma naught equal to sigma b. That means it produces the sigma minimum equal to 0. Here it is the same nature. But here sigma naught less than the sigma b. That means here bending stress is greater than the direct stresses. It will be formed two different natures. This is the compressive nature. This is the compressive nature. And here bending nature. Here tensile. Here tensile. Here it is compressive nature. Here it is bending nature. Okay, thank you. Next class we will furtherly discuss next topics. Thank you.